So what we're going to do today is a mixture of kind of like review chapter 1. There was a lot in chapter 1 that we covered, a lot of like different topics that seems like they might be kind of scattershot. They do have kind of like this underlying theme to them. And so I wanted to spend a little bit of time today kind of showing you what we were just able to do. Like, you know, with the knowledge that we just gained, what can we actually do and say about chemistry? And then at the end, we'll start into chapter 2 here. Okay, so again, we're going to want this little cheat sheet. If you ideally you have this already in your mind and you understand it. If not, then for today we can refer back to this. But again, this is just a really important relationship where if you see an oxygen with one bond, you know that it has 3 lone pairs and a formal charge of -1. Okay, so being able to fill in those lone pairs is going to be something that's really helpful. Okay, so I'm going to first put down a like a chemical equation with condensed structures. And I want you to give me the structural formula, right? So the Lewis structure of these molecules here. Okay, so. Okay, so here's just like a standard chemical equation. This would be an acid-base reaction. I'm sure you've heard of acid-base reactions in your previous chemistry course. We will be talking about them in the context of organic chemistry as well. But again, just to sort of show what we can do here, I want you guys to first convert this into a Lewis structure of each of these molecules here. And then you can go in and add your lone pairs. All right, so I'm gonna give you guys like a little bit of a head start, and then I'll start putting it in, filling it out myself here.
Kill myself.
All right, and so hopefully this is the Lewis structures that you got. Remember, this COOH is like the condensed structure code for this functional group here, what we call a carboxylic acid, where you have a carbon double bonded to an oxygen and then single bonded to an OH group. All right, and then you're going to take your Lewis structures and you're going to go in and fill them in with the lone pairs that are missing. All right, so all these oxygens that have double bond or have two bonds, they'll just get two lone pairs. That's oxygen in its happy formal charge of 0 state. This nitrogen with 3 bonds will have 1 lone pair again in its happy formal charge of 0 state. This oxygen has 2 bonds. So now I have this oxygen that has just 1 bond and this negative charge. So everybody in the chat, tell me how many lone pairs should I be putting on that oxygen? This one here. All right, so if oxygen has a negative charge, that means it has 3 lone pairs. And then this nitrogen has 4 bonds, which means that it has a positive formal charge and no lone pairs. Okay, so we've just sort of converted what was, you know, this sort of one-line chemical equation here into our Lewis structures. We've drawn in all the lone pairs and all the bonds, put in all our formal charges. Now we're going to play the spot the difference game. Okay, I want you to identify what bonds are broken. And what bonds are formed. What atoms, have moved. And do any atoms have any more or less lone pairs than they did on the reactant side? Okay. All a chemical reaction really is, and I mean, that's not to say that it's something simple, but is the making and breaking of bonds, right? So you're changing who's bonded to who in every chemical reaction. So if we can see what bonds are being broken and what bonds are being formed, what atoms have changed, who they're bonded to, we can make more sense of what's going on in this reaction here. Take a second and see if you can label bonds that are broken, bonds that are formed, any atoms that have moved. And do any atoms have more or less lone pairs than they used to? Okay. In particular, I think this one is kind of the key to being able to start to understand what's going on in this reaction. Everybody in the chat, see if you can identify which atom has moved, meaning like moved from one structure to the other, which one's changed its bonding partners. Right? So the essence of this reaction here is this hydrogen used to be bound to this oxygen and is now bound to this nitrogen, right? And again, if we do our bonds broken and bonds formed, this bond right here is the one that's broken, and this bond right here is the one that's formed, right? So that's how we can sort of see that that hydrogen is being moved from that oxygen to that nitrogen. So being able to see that is kind of the key to being able to understand what this reaction is all about. Okay. I just want to also say it doesn't matter which hydrogen I picked. I mean, I was trying to do continuity because there wasn't one on this side. I didn't have to draw the lone pair on the side here. I could have drawn it on the top. The sort of orientation, if you rotate each of these structures 90 degrees or 180 degrees or something like that, It's still the same structure. It's just rotated around. I did it in such a way that I know, because I kind of know where I'm going to go with this. But nonetheless, if your picture looks slightly different, that's not an issue. If your lone pair is on top, it's number of bonds and number of lone pairs that's really crucial for these Lewis structures. Okay, so now we've identified like what's changing what here. This is where we can use our electron pushing arrows to really show what's going on in this reaction. So we've identified what bonds are broken and what bonds are formed. Now we want to sort of focus on do any atoms have more or less lone pairs than they used to, right? Meaning if we look on the right-hand side of this reaction, do any of my atoms have more lone pairs than they did on the left-hand side? Do any atoms have less lone pairs than they did on the left-hand side, right? So one atom in particular has one extra lone pair on the right-hand side compared to the left-hand side. What atom is that? Okay, yeah, so that would be oxygen here has this extra lone pair on the right-hand side that it doesn't have on the left-hand side. Okay, so what our electron pushing arrows, what those curved arrows really help us represent is where the heck did that pair of electrons come from? Well, it used to be this bonding pair of electrons here. Okay, when this bond was broken, this oxygen takes this pair of electrons that used to be a shared pair of electrons, and now it's a lone pair. So we see the bond gets converted to a lone pair of electrons. Okay, likewise, we have the exact opposite with our bond that's formed. Which one of these elements has one less lone pair than they did on the left-hand side? All right, so we can see the oxygen's gaining a lone pair, the nitrogen's losing a lone pair. Well, where the heck did this lone pair of electrons go? It's what becomes that new bond here. And that's what I can represent with my curved arrows, where this nitrogen is reaching out and grabbing that hydrogen. Remember, you want to imagine that you're grabbing these electrons. If you're connecting two things with your curved arrow that at one time were not connected, that's forming a new bond. Okay, so our in green here, we have electrons going from a lone pair to a new bond. And in orange, we have the exact opposite. We have what were formerly bonding electrons going to a lone pair. Okay, so our chemical equation shows us like what reactants combine to make what products, right? When we go like a step further and actually draw what we call the mechanisms, so this would be the actual mechanism of this reaction. This is the chemical equation, kind of the first piece of information about any chemical reaction. We can go one layer deeper and show the mechanism of the reaction that shows how the electrons are flowing. Okay. Now, if you hate chemistry, that's just a pain in the butt extra step. If you like chemistry, that's super cool, because now you can kind of start to understand why these reactions are actually happening. Reactions are just all about making and breaking bonds. Bonds are electrons that are being shared, right? So you're actually showing the movement of electrons in a chemical reaction. Okay, so just to kind of tie the things together that we had been working on in our first chapter, kind of developing these skills and how they can kind of tie together to help us basically say more about chemistry, because that's a lot of where we're going here, right? Is to go a little bit more in depth than what we've done previously. Okay. So we're gonna do another one, and I want you guys to try to to do your best to put in our curved arrows here from this chemical equation that's given. All right, so step one. Give me the Lewis structures, or the structural formulas, as our owl likes to say. Step two, draw in lone pairs. Step three, identify bonds, broken, formed, moving lone pairs, or moving atoms rather, moving atoms, and change in number of lone pairs. And four, draw those electron pushing arrows. All right, so again, I'm gonna give you guys a bit of a head start, and then I'm gonna go in and start writing in the answer. Okay, so we talked about oxygen in the last example. What about chlorine? Does chlorine have any lone pairs? How many lone pairs should chlorine have on the left-hand side compared to the right-hand side? Let's see it in the chat. All right, so remember, chlorine, based on where it is on the periodic table, has 7 valence electrons. So it only likes to form one bond. That means that when it has that one bond, it has 3 lone pairs. That makes, right? It's got, chlorine's not hydrogen, which is the only one that can only have the 2 electrons. It's got to have its complete octet. So if it's got one bond, it's got to have 3 lone pairs in order to get that complete octet. The chloride ion means that it's accepted an extra electron, gotten to that, like, right? They want to get to that noble gas configuration. So this is actually chlorine that will have a complete octet of lone pairs, or 4 lone pairs. Okay, so I'm gonna give you guys a few minutes to finish off these last 2 here. See if you can't get all the way to drawing our arrows. I understand that's the hard part. That's what we're trying to review here, but yes, first identify bonds broken, what atoms have moved, and draw any changes in the number of lone pairs, right? This is what I affectionately call the spot the difference game. All right, so this is another example of an acid-base reaction where it's this proton, this hydrogen, that's changing who it's bound to. Okay, we can see that this oxygen has an extra lone pair on this side. Right, so where did that lone pair go in this reaction? Well, it ends up becoming this bonding pair of electrons here, because this is my bond that was formed in the reaction. So I can represent that like that. Make sure that the base of your arrow is at a pair of electrons. So if you drew it from the hydrogen to that pair of electrons, that would be wrong. It's always at the base of the base is always at a pair of electrons. And then likewise, if I go over and look at chlorine, chlorine has this extra pair of electrons on the right-hand side. So where did that come from? That was originally a bonding pair of electrons between hydrogen and chlorine. And so we would have to draw that bond breaking. Boom. Right, because this was the bond that was broken. Oops.
I have a quick question.
Yeah.
Would the arrow ever go from like the hydrogen to the lone pair on the oxygen?
No, because the base of the air, so you would kind of be drawing that those two were connected correctly, but the problem is that the base of the arrow has to be at a pair of electrons, and that hydrogen doesn't have a pair of electrons to form that bond, right? The bonding pair of electrons used to be the lone pair on the oxygen, so we have to represent that as that lone pair being the one to reach out. Right, so the pairs that I've colored here, the ones in orange and the ones in green, those are the same. It's just that what used to be a bonding pair of electrons, what used to be a lone pair of electrons in orange became a bonding pair, and what used to be a bonding pair in green became a lone pair. And actually, a really easy way to make sure that you're drawing your mechanisms correctly is your arrows should always flow in one direction. They should never kind of like bunny ears in at one another or kind of like split out and point in different directions. There's always going to be this like flow of electrons in one direction. So we can see that as well in our previous example. All of our arrows are kind of pointing in the same direction. That's a really easy way to make sure that to like kind of double check your mechanism, because electrons tend to flow in one direction in a reaction.
Will those arrows always be on the same side as well?
They will always be on the reactant side, if that's what you mean.
Yes.
Because we're always, yeah, because what we're really representing is how did these reactants turn into products? Right, the flow of electrons that led to our particular product. And again, electrons tend to flow in one direction. So that's just a really easy check to make sure that we're doing it correctly. Okay, so these arrows I know are a sticking point. When we get to the portion of each chapter where we're dealing with mechanism, I'll make sure to do a bunch of examples and stress it and all that good stuff. But again, it's that much extra of a piece of information. It's one thing to know what reactants turn into what products, and it's this extra bit of information to be able to show how the electrons are flowing in a reaction. Okay.